Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. The title of this lecture is Max von Laue formulation of crystal diffraction. In previous lecture, we discussed Bragg's law and its importance in crystallography. We also discussed the basic statement of Bragg's law, which states that the existence of crystallographic planes is necessary in order for diffraction to happen. But Max von Laue stated that the existence of crystallographic planes is not necessary. Okay, even this can happen from a couple of atoms as well. So this is I think the basic difference between Max von Laue formulation and Bragg's law. Or we can say that Bragg's law is a specific case of Max von Laue formulation. Max von Laue was a German crystallographer, and he was born in 1879 and died in 1960. He also received the 1914 Nobel Prize in Physics. So let me read this text for you and then we can push it forward. Max von Laue formulated an alternative consideration to the Bragg's law for diffraction. This theorem or this notion is beneficial because it doesn't require the assumptions used by Bragg that reflection is specular and involves parallel planes of atoms. So this is the one I just said, that the reflection is specular. Specular means mirror-like. Okay. That's why sometimes this diffraction is called reflection. And according to Bragg's law, this diffraction requires crystallographic planes, whereas according to Max von Laue formulation, it does not. So as far as the basic points and features of this formulation are concerned, they may be stated as number one, no parallel crystallographic planes are needed. As I told you, we can have just a couple of atoms in order for diffraction to happen, and the crystal is composed of identical atomic objects at the Bragg lattice sites, and each atomic object re-radiates the incident wave in all directions. And number four, diffraction peaks or diffraction spots will be observed in directions where rays scattered from all lattice points interfere constructively. So the basic theme of this formulation is that if an atom is bombarded with an electron beam or an electromagnetic radiation of proper wavelength, then this atom re-radiates similar beam of similar wavelength in all directions. So same can happen with all the atoms. So it means that the two beams re-radiated from at least two atoms in all the directions, they produce an intense spot where they interfere constructively, and nothing where they interfere destructively. So this is the basic theme of Max von Laue formulation. So as is stated in here, the simplest approach to Bragg diffraction is illustrated in figure. We assume a specular reflection with angle of incidence equal to angle of reflection. Okay, the figure is shown in the coming slide. I will display it to you shortly. We also assume the radiation is elastically scattered so that incident and reflected waves have the same wavelength and of course energy. Okay, because we may have an elastic scattering, we may have an inelastic scattering. So for the Laue condition, to make the case more simpler, we presume that this scattering is elastic. So this approach is thus useful, which gives the physical picture of the constructive interference. So for constructive interference, we must have the path difference between reflected rays equal to an integral number of wavelength. So the condition for diffraction peaks is then 2d sine theta is equal to n lambda. So now in the next slide we are trying to prove Bragg's law from mix 1 Laue condition, and this is very simple as you see in here. As I told you, mix 1 Laue condition or formulation is more general and more broad compared to Bragg's law, and if this is the case, then Bragg's law can be simply verified, derived from this condition. Okay, now let's consider an atomic plane. So this dotted line can be presumed to be an atomic plane or crystallographic planes. Okay, so we can consider an atom in here, okay, or just one atom, and this is the incident beam, right? This is the incident beam, okay, making an angle theta with this plane, and once this beam interacts with the lattice point or atom or molecule that is accommodated in here, then this is scattered. Part of this beam is scattered in this direction. Though I have told you that we have the scattered beam in all possible directions, but we have only considered this specific direction, right? Otherwise we can consider any direction in here. So this is angle theta, and the scattered beam 2 makes an angle theta with the atomic plane, and this is represented by k naught. This is the wave number, as you know, this is 2 pi by lambda or 1 over lambda. Okay, and this is k, again another wave number or the scattered wave, which is again 2 pi by lambda or 1 over lambda. As I told you that this scattering is elastic. Okay, so this k naught and k are the same, and this is the difference between the two vectors, which is delta k. This is just simple vectorial summation, and from this vectorial summation you can say that this is delta k, okay, which is k minus k naught, right? So k naught is equal to k is equal to 1 over lambda, right? And this is quite clear, and k naught plus delta k is equal to k, as clear from vector summation. These two vectors are added together to give you this k. Okay, so this is k naught plus delta k is equal to k, and taking square on both sides of this equation, we can get k naught plus delta k whole square is equal to k square. And then by applying the basic formula, we can have k naught square plus 2 k naught delta k plus delta k square is equal to k square. And as k naught is equal to 1 over lambda, and so is k, so just substitute the values of this k naught and k, then 1 over lambda square plus 2 k naught delta k plus delta k square is equal to 1 over lambda square. So these two lambdas, these two guys, okay, can be cancelled out mutually with each other, and we are left with the 2 k naught delta k plus delta k square is equal to 0. Okay, so I'm hopeful you would have got clear picture until this equation. Now, as you know, the reciprocal lattice vector is always perpendicular to the atomic plane. So this is the atomic plane, and this vector, if this is the vector, right, which is normal to this atomic plane, this can be G, which is the reciprocal lattice vector. And this G and this delta k, they are basically in the same direction, and this delta k too is normal to this atomic plane. Okay, so that is why we can put this delta k equal to this G. Is it clear? Look, we have just shown a part of this figure. This is k naught, which is shown in here, the incident angle and the atomic plane, and this k naught is equal to k, and basically the angle between G and this k naught or k is equal to 90 plus theta. Okay, so considering this substitution, we can have 2 k naught into G plus G square. Okay, from here this is equal to 0, and then k naught dot G is equal to k naught G cos of 90 plus theta, as clear from this figure. If we consider the dot product between these two vectors, then we can have magnitude of one vector into magnitude of another vector into cosine of the angle between the two, which is 90 plus theta. And so k naught G is cos 90 plus theta, and k naught dot G is equal to minus k naught G sine theta. Okay, because cos of 90 plus theta is equal to minus sine theta, and minus 2 k naught G sine theta is equal to minus G square. Okay, it's I think it's clear. Once we consider this equation, 2 k naught G sine theta, just multiplying minus 2 or 2 in here, so this is minus 2 k naught G sine theta is equal to minus G square, and then 1 over lambda sine theta is equal to G, and we have because we have k naught is equal to 1 over lambda, Okay, and here these two are simplified, giving G on the right hand side, and we have 2 1 over lambda sine theta is equal to 1 over d HKL. Do you remember that reciprocal lattice vector is equal to the reciprocal of the interplanar spacing? So we have replaced this guy with 1 over d HKL and 2 d HKL, right? Sine theta is equal to lambda, and just introducing the order of diffraction, which is n, then this becomes more general equation, because in most of the equations we use in XRD machines we put n is equal to 1. So this is the general form of the Bragg's law. So it means that we can derive Bragg's law from the mix von Laue formulation. So hopefully you have grabbed that very well. Okay, so let's move to a numerical problem. The numerical problem is quite clear. This is we have considered a crystallographic plane with intercepts x, y, and z, and the intercepts are at x1 a1, x2 a2, and x3 a3. These are the components, okay, x, y, and z components of the vector. Okay, and then we can write x1 ratio x2 ratio x3 is equal to 1 over h ratio 1 over k ratio 1 over l. Okay, so the question is, prove that the reciprocal lattice vector, which is hb1 plus kb2 plus lb3, is perpendicular to this plane. As I told you in the previous slide, that the reciprocal lattice vector sometimes represented by g in the uppercase, sometimes g in the lowercase. So this is hb1 plus kb2 plus lb3. In certain books you can find the notations as h asterisk plus kb steric plus lc steric in some books. So you don't have to be confused in that. Okay, so we have in here a1, a2, a3 as the direct lattice vectors, and b1, b2, b3 as reciprocal lattice vectors. So we have considered two vectors within the plane, and the two vectors are x2 a2 minus x1 a1. So this is a vector that lies in the plane HKL. Okay, and this is another vector which is x3 a3 minus x1 a1. This is another vector in the plane. So if the product, I mean the cross product of these two vectors gives the equation of the reciprocal lattice vector, then it means that the condition of perpendicularity is fulfilled. And so this is the cross product, and the final outcome of this cross product is hb1 plus kb2 plus lb3, because we see that from this cross product, just from these simple substitutions, okay, we can obtain h, and then we can obtain k and l as we have written in here. okay, from these ratios. So the final equation we get is related to the reciprocal lattice vector, and this is the diagrammatic representation of what I told you, that if we have an HKL plane like the one you see in here, and then the OA vector will be A by H. A by H is basically the intercept, I mean the x-intercept. OB gives you the this is another vector OB, and gives you the y-intercept, and similarly the z-intercept. Okay, so if you want to prove this problem, okay, that the perpendicularity of the reciprocal lattice vector with the HKL plane, then you can prove it quite simply from this diagram as well. So what this diagram says is right, the vectors OA, OB and OC have lengths A by H, B by K and C by L, and the vector ON, which is this is the ON which is perpendicular to this HKL plane, and because the unit vector is in this direction, so this can be written as in the form of a unit vector as well, and the reflection G associated with diffraction from the HKL planes is parallel to N and normal to all vectors in HKL. So what you have to do is that you can choose the vector AB, or you can choose the vector AC, or you can choose the vector BC. It's up to you. So for example, you choose the vector AB, which is the vector of the HKL plane. So this comes out to be B by K minus A by H, and then you can take the dot product of this vector with the G, okay, which is H asterisk plus KB asterisk plus LC asterisk, and this will give you straight away a 0. Okay, so it means that these two vectors are perpendicular to each other. Similarly, you can take AC, which comes out to be C by L minus A by H. Okay, so this vector becomes perpendicular to the G vector if its dot product gives you 0. Okay, and similarly you can take BC and then its dot product with the G, and this will give you a null result, and this will prove that these two vectors are perpendicular to each other. And again, a simple problem that the distance between two adjacent parallel planes is equal to 2 pi by G. Okay, again we can take any vector, this vector x1 a1 plus x2 a2 plus x3 a3. This is a general vector, you can take it, and then the expression, this is exponent iota g dot r. This is always a constant, since the lattice constant, this is the origin, and this is the lattice which contains this vector. We obtain exponent iota g dot r is equal to constant, and this constant is equal to 1. Okay, So this vector belongs to the HKL plane, so does this vector, and which is the origin. So therefore G dot R is 2 pi n, and G delta R is equal to 2 pi delta n, right? So I mean, if this is G dot R is equal to 2 pi n, then we can have G dot delta R is equal to 2 pi dot delta n, just the difference between the two vectors. And this n is the order of diffraction. So the distance between two adjacent parallel planes, if we have two adjacent planes, then the order for these two adjacent planes is equal to 1, and then these so we can have this is a G vector over G modulus, and to delta R is equal to 2 pi by G. Why? Because this delta R is basically this is equal to G dot delta R. G dot delta R is basically 2 pi delta n, and delta n is equal to 1 if the planes are adjacent, and then we can have 2 pi by G modulus. And this is another simple technique that you can prove the same result from this technique. And hexagonal space lattice, these are the lattice translational vectors for the hexagonal space lattice. What you have to do is just to calculate the volume A dot B cross C. So in here this becomes A1 dot A2 cross A3. Okay, you just find out this expression, and then finally you will get this volume. And the other thing is you know the linkage between direct lattice vectors and the reciprocal lattice vectors. Okay, and then you can find out this result. This P1 comes out to be 2 pi by 3 power 1 over 2a, and this is x hat plus 2 pi by a y hat. Similarly B2 and B3. And describe and sketch the first relevant zone of the hexagonal space lattice. So this is the first part of the problem which you can prove easily, and the second part of the problem, this is the linkage between direct lattice vectors that are A1, A2 and A3, and the reciprocal lattice vectors P1, B2 and P3. So the cross product and the volume you calculated already, so you can put this volume in here, and then you can calculate the cross product from this determinant and the final result. So you can calculate it for B2 and B3. As far as the relevant zone is concerned, then this is a sketch because the lattice is hexagonal, so a simple hexagon is shown, and this point is specified as the origin, and then you can join the nearest neighbors to find out the relevant zone, and then from every distance from the origin a normal is passed through the midpoint of every joining line, like the one in here. So similarly in here, similarly in here, and so everywhere. And then this volume that is enclosed, this gives you the first relevant zone. So we have 6 vectors. Okay, so the broken lines are the perpendicular bisectors at the midpoints as written in here. The inscribed hexagon forms the first relevant zone, and it comes out to be 2 pi because the volume becomes B1 dot B2 cross B3. b1 dot b2 cross b3. So just put the values of b1. This is the value of b1. So b1 dot b2 cross b3. So b1 is 2 pi into a2 cross a3 divided by a1 dot a2 cross a3. So this is b1. b2 becomes a1 cross a3 divided by a1 dot a2 cross a3 with 2 pi. And similarly b3 becomes a1 dot a1 cross a1 cross a2, okay, divided by a1 dot a2 cross a3. So you just take these expressions and then put it in the equation for volume, then you will get this equation and eventually this. So you prove this simply, and this is the same method that's used in here. Okay, so this is the distance between adjacent planes, right? Distance between adjacent planes. You just read these simple mathematical calculations and then and a simple algebra, then you can arrive at this equation. This is very important. You know, we can have some crystals that have sodium chloride like structure, and some crystals that have cesium chloride like structure. As far as the cesium chloride like structure is concerned, this is simple body centered cubic structure. This is body centered cubic structure. This is called cesium chloride structure. And other crystals that have the same structure are copper sulfide, cesium carbon nitride, etc. And the crystals that have sodium chloride like structures are sodium chloride, potassium bromide, silver chloride, magnesium oxide, etc. So from the radius ratios of cation to anion, okay, we can make an educated guess which type of structure it is. Okay, as far as the cesium chloride like structure is concerned, which is the body centered cubic structure, we can have a very simple calculation. This is BC, which is equal to the side length of this cubic structure, and this is AB, right? The facial diagonal, this is equal to a square plus a square, which is 2a square by Pythagorean theorem, and AB comes out to be under the root 2a, and this is AC, the body diagonal length, which is AB square plus BC square. So this is a right angle triangle, and applying similar Pythagorean theorem on it, we get 2a square plus a square is equal to 3a square, and AC is equal to root 3a, okay, from this equation. And then AO, which is the half distance until here, AO, which is the half distance, this comes out to be root 3 over 2a, and this A from this equation. This A is equal to 2r minus. R minus means that this radius corresponds to the A9 radius, and this is A9 as written in here. This is A9, this is A9. Okay, and as far as the side A is concerned, this is equal to sum of the two radii, like the one in here. One radius and then another radius of A9, so this is 2r minus. Okay, so just put this 2r minus in this equation, then we can have root 3 over 2a is equal to basically this is r plus r minus. Okay, for this is the half distance that you calculated from here, and this half distance is also equal to one radius of A9 and one radius of cation. So this is cation, and so this is cation in here. So this is r plus r minus, and this r plus r minus is equal to 3r minus, and eventually we get the radius ratio of cations to anions. This is 0.732. so this is the minimum ratio that a crystal can have in order to adopt the cesium chloride like structure. So this is a very straightforward, again this is sodium chloride like structure, which is face centered cubic structure, and even one face is shown in here. This is anion, this is cation. This distance, this is the facial distance, the facial diagonal distance. This is equal to 1 anion radius, 2 anion radius, 3 anion radius, and 4 anion radius. Okay, so this 4r minus is basically equal to the square of this side. I mean the square of this side is equal to the square of this side. This side, you know, this is 2r minus plus 2r plus, and same for this, and so we can have this expression, and then this ratio, which comes out to be 0.414. so ionic crystals with radius ratio greater than 0.732, as I told you, this was the minimum radius, so that these types of crystals have cesium chloride like structure, and the ionic crystals with radius ratio which is between 0.732 and 0.414, they form a rock salt like structure. So hopefully you would have got that. So soon another video will follow, and God bless you. Allah Hafiz.